All right. So welcome back, everyone. I hope everyone is refreshed and sufficiently caffeinated. So I'll introduce the next speaker. Our next speaker is Professor Ippei Obayashi from the Center for Artificial Intelligence and Mathematical Data Science at Okayama University. And he'll be talking to us about Home Cloud, which is a software I also use for my own research and teaching. Home Cloud, a persistent homology-based data analysis software. So please.
Thank you. Thank you for the introduction. Yeah, I'm Obayashi, working in Okayama University. In this talk, I will talk about Home Cloud, uh, our software for persistent homology. This is a short introduction, the self-introduction. I'm an applied mathematician that is interested in research that combines computers and mathematics. And I'm very interested in these research topics, such as topological data analysis, persistent homology, dynamic systems, and applied statistics. This slide shows the contents of this talk. First, we will start to persistent homology. Probably, some people in the audience are experts of persistent homology, and others are not so familiar with it. So I start from the introduction to persistent homology. Persistent homology is a part of topological data analysis, which is data analysis methods using the mathematical idea of topology. And topological data analysis, shortly TDA, enables us to quantitatively characterize the shape of data using topological structures such as connected components, rings, cavities, and cavities. And persistent homology is one of the most important tools of TDA. Using it characterizes the shape of data using the idea of homology, a part of topology. And persistent homology, especially pH, gives good descriptors or future values for the shape of data called the persistence diagrams or persistent barcodes. The research or persistent homology starts from in the start of this century, 21st century, and quickly developed from mathematical theory and algorithm software to application to material science and life science and many other fields. Okay, topology and homology is a mathematical framework to characterize or formalize some shapes such as rings and cavities from mathematical viewpoint using algebra. Especially in the theory of persistent homology, linear algebra is usually used for the formalizations. And in homology theory, the structures, the topological structures are classified by a kind of dimension. This is zero-dimensional structure, or the zero-dimensional structure is in the homology theory is the connected components. One-dimensional structure is ring structures, and two-dimensional structures are cavities. For example, there are in this figure, there are two shapes. One is a cylinder, and another is a balloon. And cylinder has cylinder is looks like a hole or looks like a ring, and the cylinder has one-dimensional hole here in this here, and cylinder is also a kind of connected component, and cylinder has one zero-dimensional homology. Balloon has another kind of hole, kind of or voidal cavities, and so balloon have one two-dimensional homology. Okay. This is the ideal basic concept of homology, and now we will move to the idea of patient homology. Now we consider this type of input data, and this is a set of point. Such a data is called a point cloud, and this point cloud has no holes or rings, but it looks like it seems to have two rings here and here. To realize the topological structures on this point cloud, we put disks or balls with the same radius, like in the right figure. In the right figure, there are two rings here and here. The topological structures are realized by connecting the points in this figure. The problem here is to determine the radius of the disks. If the disk is too small, or points are disconnected. But if the radius is too large, the hole here disappears by freeing the internal. The fundamental idea of patient homology is to consider increasing process of disks instead of fixing the radius. For example, in this example, from left to right, the size of disks the size of disks becomes larger from left to right, and in this increasing process of disks or increasing process of geometric object, some ring appears and disappears. In this figure, a ring appears here, and this ring is called X. And the ring X persists in this process and finally disappears here. Another ring, Y, appears here. And this ring quickly disappears here by the change of the size of disks. And using the mathematical theory of patient homology, we can make pairs of appearance and disappearance of rings. In this case, a ring appears here, disappears here, and another ring Y appears here, disappears here. And such pairs are called basis pairs. And we use the pair of appearance radius and disappearance radius is as a characterization of the shape of data. Here, a ring appears at whose radius appears here mm, when R is B1 and disappears R is D1, then we characterize this ring X using the pair of B1 and D1. Another ring Y is characterized by using the pair of appearance radius and disappearance like this, R's and B's and D2. And the set of such a birth radius and death radius is called persistence diagram. And we often visualize the persistence diagram using this kind of the scatter two-dimensional scatter plot or the hissue. Yeah, theoretically, we can define the persistence diagrams for any dimensional data, any dimensional point cloud. But in practice, we often compute the persistence homology for two-dimensional or three-dimensional data because two-dimensional or three-dimensional data is easy to treat. Because this is because high-dimensional hole in high-dimensional data are difficult to understand in our brain. Some mathematician can imagine such a high-dimensional hole easily in his or her brain, but many people cannot such many people does not have such a imagination. So, and another reason for using such a two-dimensional or three-dimensional data is the for efficient computational techniques. Especially, three-dimensional data is suitable for persistence homology, since such a characterization of three-dimensional data is difficult, more difficult than two-dimensional data. And persistence homology can also apply to various increasing sequence other than point clouds. Or one typical application of persistence homology is to analyze image data, binary image data or the grayscale image data. Especially three-dimensional image data kind of voxel data, such as X-ray CT images are suitable for the analysis by persistence homology. Okay, this is the outline of persistence homology. And next, I explain the basic idea, basic mathematical concept for persistence homology. In the mathematical theory of persistence homology, the first data is first we consider various type of input data, a point cloud or an image or another type of data, and from such a input data, we construct an increasing sequence of geometric objects, such as simplicial increasing sequence of simplicial complexes or cubical complexes, as shown in this figure. In this figure, the simplicial complex becomes larger from left to right. And from this geometric model, and by applying homology functor, we get the sequence of homology groups. This is quite mathematical operations. And from the sequence of homology groups, we can obtain the persistence diagrams as shown before. This is a mathematical framework for persistence homology. To implement persistence homology to the computer, we need to interpret this mathematical framework for computer. In this figure, the algorithmic framework for persistence homology is shown. From the input data, point cloud one image or other type of data, we construct a geometric model. This is the increasing sequence of simplicial complexes or cubical complexes or other types of complexes. And this part is almost same as the mathematical framework. And next part is a bit different. In the theory of persistence homology, the sequence of homology group is constructed, but to implement the algorithm to the on the computer, we compute the matrix of boundary maps, and from the matrix we apply matrix reaction algorithm, and finally we obtain this persistence diagram. For example, this figure. So this slide shows the example for a point cloud. From a point cloud, we first construct a drone triangulation. なんかこの通然間違ってる気がするな。まあいいや。And this is a kind of a triangulation of the point cloud, and the output is the simplicial complex. And we also compute the alpha bars or birth radius for this drone triangulation. And as a result, we obtained the alpha values for each simplex. This value is the radius of minimal enclosing balls of the simplex. As shown, this is an example of alpha values like this. And from the drone triangulation and alpha values, we construct a boundary matrix like this. And for the computation of this matrix, the simplices are ordered by the alpha values, and the boundary matrix for it and the boundary operator is applied to each simplex. And we consider the combinatorial relations between simplices, and finally boundary matrix is constructed. From the from this matrix, Bass's pairs are computed. And in this output is the pair of Bass simplex and Death simplex. And finally, these simplexes, these simple are replaced by alpha values. This is the Bass's pairs used in the practical applications. The computation process for grayscale bitmap data is similar. From a grayscale bitmap data like this, we compute a cubical complex. This is a kind of cubical complex, and we also compute the levels of all cubes like this. And using a cubical complex and levels, we compute the boundary matrix. We construct a boundary matrix, and the Bass's pairs are computed from the matrix by applying matrix reduction algorithm. To compute the persistence from data, we need to construct a called geometric data, a kind of increasing sequence of simplicial complex or cubical complex. Such a sequence is called often called iteration. And for the application of partition homology, some filtrations are proposed as shown in this slide. For a two-dimensional or three-dimensional, or probably four-dimensional point cloud, alpha filtration is usually used. From a distance matrix, a bit ellipse filtrations is used. For digital images, cubical filtrations are used. If the data is a grayscale image, the filtration is directly computed. And the data is a binary digital image. We compute the binary image data is converted by a distance transform. And from the distance transform, we compute the cubical filtration. Here, I do not explain the detail of the distance transform. If you want to know about this technique, please please examine by yourself. Sorry. Another type of geometric model is also available if such a if the boundary matrix and the levels are explicitly given. And from now, I do not explain the algorithm algorithms about for partition homology, especially for I sometimes say matrix reduction algorithm, and this is the simplified version of the algorithm. This is the basic partition homology algorithm. This is called this is often called left to right reduction algorithm. Yeah. In this algorithm, a matrix is reduced. Column reduced. This is the column reduced algorithm. and 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 this very in some sense very simple algorithm gives such a complicated output of Partition topology. Some introductory textbook will explain why this algorithm gives the correct answer. Some textbooks, such as written by Edesbrunner or Hara or some other textbook will explain why this algorithm works. Okay, now I switch to the introduction to HomeCloud, our software to compute, persistence, and analyze the data using the ideal Partition topology. And now in this world, there are much software for Partition topology. As shown in this slide, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or more. Depending on each researcher's interest and analysis target. For example, these three software, DFA, FAT, and RIPS, are developed by the same people, and these the developers are very interested in the efficiency of the algorithm. So, and these softwares are considered to be a kind of most efficient software in the world. And many other softwares are there are many other softwares like this. And HomeCloud is our Partition topology-based data analysis software. You can download you can see the documentation in this URL from this URL. HomeCloud starts in 2015, and when the development of HomeCloud started, I am a researcher in the research center for material science. So the HomeCloud start for the applications in material science. The target data is molecular dynamical simulation data or image data from the electron microscope. Of course, that for any other fields is available. You can apply HomeCloud your own data. And the interface, HomeCloud has a Python interface. HomeCloud also have a command line interface, but I recommend the Python interface. And HomeCloud has various features such as visualization, machine learning, and inverse analysis. Inverse analysis is HomeCloud's the most important feature, I think. And HomeCloud accepts various types of data as input, such as point clouds or images and distance magic. HomeCloud works under these environments. Linux, OS, Mac, and Windows, and Google Cloud. This is the kind of Linux, but it works on a Google server, and we don't need a complex installation process or the Python system. We need is only what we need is only a web browser and a Google account. And but we also home cloud can be used for can be used on your laptop or server machine. You can install home cloud through PIP. This is the standard Python package manager command. This is a history of home cloud. Home cloud starts in 2015, and before 1.0.0, main features of home cloud are implemented. In 2018, version 1.0.0 is released. After that, the total software was under open software license, and the all components of the software is publicly released here in July 2018. And after that, in the same year, the version 2.0 is released. After that, this is the important version 3.0.0. In this version, the architecture of home cloud is redesigned, and Python interface became mainstream. And the development continues and have continued, and the latest version of home cloud is 4.7.0. This version is released on March. Here I show some features of home cloud. Home cloud accepts various kinds of data as input. Point clouds, grayscale image data, distance matrix, abstract signature complex with a map from a simplest to real value, or boundary map. These kind of input data are available. Home cloud, of course, can plot persistence diagrams as shown in this figure. You can change the configuration or visualization. For example, range and number of beans and titles. And this visualization is not satisfactory. You can retrieve the list of births and deaths, births pairs, and plot it as you like using your favorite software. Inverse analysis is one of the most important features in home cloud. This is functionality enables us to find a topological structure corresponding to a basis pair. For example, from a point cloud, we can compute a persistence diagram, and from a single basis pair, we identify the structures, rings or cavities corresponding to each basis pair. We can in home cloud, there are some kinds of inverse analysis methods shown in this slide. The first and most often used feature is the optimal or stable volume. This is a standard way for inverse analysis, and we can apply to can apply optimal and stable volumes to simple shell or cubical filtrations. And stable volumes is a kind of updated version of or improved version of optimal volumes to treat noise. And the developer of home clouds recommends the stable volumes for general usage. Patient homology tree, PH3, the another inverse analysis method. It has the information about the tree relationship between volumes. That is, they have richer information than optimal stable volumes. But patient PH3 have another restriction. We can apply PH3s for only for the limited data, limited patient homology shown in this figure, because PH3s utilize the Alexander duality and the patient homology for connected component. And another home cloud feature is the vectorization for machine learning. Home cloud provides histogram-based persistence diagram vectorization methods such as persistence image and persistence codebook. These two methods, both of these methods are based on histogram, persistence diagram histogram, and now we recommend the use of persistence image because of its simplicity. Okay. Next, I explain the design principle and architecture of home cloud. From the user's viewpoint, the home cloud follows the standard practice of the Python's semantic computing axis as much as possible. The most important practice is using the NumPy's ND arrays. This is the standard implementation of multi-dimensional arrays in Python. Many Python libraries use ND arrays. So, well, we can so home cloud can communicate with such libraries through ND arrays. And we, from the viewpoint of users, some standard some standard visualization libraries such as matplotlib and plotlib are used. So, by using such libraries, we can customize the visualization using the functionalities of those libraries. From the developer's viewpoint, we have three design principles. I explain one by one. One principle is using external software components to reduce the development cost. I have used the external software components if such a component are sufficiently reliable. For example, Shiga, the computational geometry algorithmic library, is used for computing alpha complex, and FAT and RIPS are used to compute persistence diagrams. And many other libraries are used. for the development of partial home call. Another, the second development principle is not a pipeline. Yeah, probably it sounds somewhat curious. Yeah. So I explain here. This figure shows the pipeline design of the partial scenario computation. Probably this design appears to be suitable for the theoretical viewpoint, but home cloud does not adapt it because we have mainly two reasons. One is that there exists very efficient software component to compute partial data for specific data, such as distance matrix or the bitmap data. In home cloud, Repsol is used to compute a partial scenario for feature strip filtrations and Homoshi Cube. This is the software for the partial homology for alpha for bitmap data. These components, in fact, do not compute the boundary matrix explicitly to make the computation faster. So, boundary map, the computation of boundary map is skipped in these software. So, such a design does not work well. Yeah. Another reason is that the impulse analysis and visualization require additional information, and it depends on input types. For example, the coordinates of point is required for visualize the point cloud data, and other data is required, as shown in this slide. So, the architecture is shown like this. Home cloud does not have a kind of pipeline architecture, but it has a parallel architecture like this. From a point cloud, simple filtration is computed, boundary computed, and percent computed, and from these from the input data and intermediate data, additional information is stored to the output file. Bit filtration have another steps like this. And instead of such a variety of computational process, OnCloud provides a unified interface for persistence diagrams. And another, probably third design principle is dog fooding. This is a practice of using one's own products, software products. And the speaker, I always use these home cloud for patient homology data analysis. This practice have these advantage. Yeah. One is the software quality can be monitored by the developer at all times. Another advantage is the usability is always tested by the developer. That is by me. And the developers can by using the software by myself, we can understand the real world usage. Yeah. For example, currently, HomeCloud has more features for alpha persistence homology, alpha filtration than beetle strips. virtualized because the main reason is that I rarely have the opportunity to use virtualized filtration, except for theoretical studies. Yeah. But we have another reason to alpha patient homology has richer features. Another reason is the Beatles Rips filtration has too many simplices, and various features do not practically work on the Beatles Rips filtrations. This is the problem of the computational cost. Okay. Now, I quickly explain the development of HomeCloud. Now, HomeCloud is development mainly by me alone. And this is the kind of weak point of this software. Probably, if I got to serious fever, the development of HomeCloud is completely stopped. This is but some people have helped with the development of HomeCloud. Some collaborators, such as Miyanaga-san, Wada-san, Nakashima-san, Dan-san, and other people can help me. And I also order some programming to outsourcing company. And HomeCloud is mainly developed under the Linux environment. In fact, in this notebook, Linux is installed, and I use this laptop for the development of HomeCloud. But continuous integration system is used to conduct tests on Windows and Mac. This is important for the development. This system ensures the portability of the HomeCloud to other systems. And this system, continuous integration system, also provides the binary package for fast and easy installation. Now, I explain how to use or how to run HomeCloud. Now, we recommend using the Python interface over command line interface. And if you want to try HomeCloud, it is best to start with Google Collaborative. And HomeCloud, on the website of HomeCloud, HomeCloud provides a tutorial. And please start with a 3D point cloud analysis for the tutorial. After completing this tutorial, you should proceed to other tutorials that interest you. And HomeCloud provides two types of documentations. One is tutorials, and another is API documentations. You can see both documentation for your application to HomeCloud, application of HomeCloud. And HomeCloud is the open source software, and you can use HomeCloud freely. But if you will publish a paper using HomeCloud, please cite this review article about Partition homology and HomeCloud. Finally, I shows the future of HomeCloud. Now we have a plan to continuous code refinement, plan for updating documents and and publishing the source code repository. I think that the code is I think code is good to organize, but some parts are not. Some parts are quite messy. So we need to organize such a code better. Of course, faster algorithm and faster implementation is required for in the future. And for the documentation, we have well-organized tutorials and API documentation. Recently, the tutorials have been reviewed and refreshed for this presentation. And the next step is to prepare code snippets. This is the kind of small code fragment to solve a single problem. The third plan is to publishing the source code repository. Now, the source code itself is available by downloading the third TDA file, but the Git repository is not available now. So we organize the repository, and we will I will publish the Git repository to the public usage. In this slide, I inside some more ambitious ideas for the development of whole class. I think parallel computations is required for optimal on stable balance, because in fact computing a persistent diagram is now sufficiently fast, I think, but computing a single volume is requires significantly more cost than computing persistence diagrams. So, but because such a features use linear programming, but I think the optimizing I need to optimize the computation, but I think it is probably quite difficult to fundamental advance, fundamental improvement. So the next step is considering a parallel computation. Another ambitious idea is supporting the non-rectangular unit cell for periodic boundary conditions. Now, rectangular unit cell supports Honeycomb because Sigma supports such a periodic boundary condition. And this is a desirable feature especially for the analysis, the kind of crystalline structures, but it is difficult to implement. The third idea is the integration with connected persistent diagram software. This is this is one of the extensions of persistence diagram using multi-parameter persistence homology. And I prepare the demo for the persistence homology. これ40分までやるよね。ちょっと、まあちょっとやってみようかな。じゃあ、OK. Now I quickly show the demo for home cloud. This is the analysis of atomic configuration data or amorphous silicon. Here, we need to install some software in addition to home cloud. This takes sometimes 30 minutes, 30 seconds or something. Please wait for something. 接続しとけばよかったな。In this demonstration, we use Google Collaboratory. If you want to use this demonstration, please visit our Homocar's website. Okay, now the installation is completed in 40 seconds. Here, we download the data from this website, and we convert the data from this format to another format. This is the input data format, and this is the converted format, a bit different. ASE is one of the atomic configuration environment software support this kind of data. Now, we read the data from here and visualize the atomic configuration like this. The visualization, Py3D model is used for the visualization. Calculate the persistence diagrams and plot it like this. Now, zoom in. This is the first one-dimensional persistence. We zoom in here like this, and we apply inverse analysis here by extracting a single basis pair, compute a stable volume, and skip here and visualize it on such this kind of not. This is a ring correspond to a single basis pair like this. We can compute this ring using Homocar's. Now, I finish my talk here. Thank you for your attention.